Hello, this is Lanaya Allen for the correlation group, and I have with me also.
Oh, hi, I'm Anne. Nice to meet y'all, guys. Anyways, we.
So we have the subject of correlation, and what is a correlation is that it is a statistical measure that indicates the extent to which two or more variables fluctuate together. The purpose and what does correlation mean is actually quite simple. The purpose is that it measures the relationship between variables, as in it's more of a might cause situation, but correlation does not mean causation, or it does not indicate cause and effect. And it also considers the strength and direction of the relationship. Some
All right, so some of the assumptions for being able to do correlation will be that both variables will have to be continuous. So you'll get a independent or dependent variable that will be continuous, as in they don't reach zero. It'll be an endless amount of numbers. Also, you need to have the absence of outliers, which would be the indication of the plus or minus 3.29 standard deviation units. Also, the related pairs. So the participants need to have a score for each variable. You also need to have homoscedasticity and linearity. Linearity. There are many different types of correlation, but since in class we only went over Pearson, that is the one we are going to really focus on. And the Pearson correlation coefficient is the relationship between the two variables measured on an interval or ratio scale. Notice the relationship is bolded.
And in order to test the significance, we need a null and an alternate hypothesis, which, as you all know, the null will always, be p equals zero. And the alternative will be p does not equal zero, p is greater than or less than zero. And then the thing that makes the degrees of freedom slightly different for correlation is that the degrees of freedom formula is n minus 2, and it's n minus 2 because we have two variables. So therefore, in order for it to be accurate, you need to take your total number of participants and subtract them from 2. For strength and direction is also actually quite simple, and kind of like how correlation does not mean causation, strength does not mean that it's better necessarily. And it's also provided by a number value anywhere from -1 to 0 to 1. And the correlation coefficient is basically the farther away from zero you are, whether it be positive or negative, the stronger it is. So, for example, if you had -89 and you had 7, -89 would be stronger than 7. And for direction, pardon me, for a negative direction, it will basically be going from a diagonal from left to right, and for a positive direction, it would be going the normal way, um, bottom diagonal from left to right, going upward. And basically, a negative correlation would mean that they're in a straight line, possibly, maybe of some sort, but it's in a negative direction, and vice versa for positive, except the numbers would more than likely be positive of some sort. But again, positive does not mean better either. It's just indicating the relationship in which the that it's going.
In this next example, we see that there is a positive correlation because the line going from left to right is tilted up. As you can see, there is a y equals number at the middle of the bar. This was also from one of our labs that we did, so this will be somewhat of a refresher. This next one, I'll give maybe 30 seconds to let you guys decide if this is positive or negative. Ready? All right. So this should have come out as a positive correlation, seeing as the line is left to right upwards with the positive number of the y equals. This next one will be kind of tricky, so giving you some more time now. All right, so since this was a tricky one, this one should have come out as a negative, seeing as the line that you could have drawn would have gone from right to left, going up in that direction from right to left. There is a positive, there is a negative relationship between all of these numbers, seeing a relative line with that.
And to even add to these examples, in the first example, it was a weak positive correlation, mainly because not all of the dots aligned with the line of with the straight line, quote unquote. But however, they were homoscedastic, meaning that the spaces in between the points were relatively equal to each other. So it would be a homoscedastic, low or weak positive correlation. And for the second example, it will also be low or weak just because the points are also more spread out than together against the straight line. And like Anne also said, since this was a strong negative correlation, it's stronger than the previous two because if we had inserted our straight line to indicate where the negative straight line would be, then the points would be roughly, if not on, very close to the straight line, making it stronger.
So r squared, which can also be the coefficient for the determination, which is essentially the effect size indicator. So when studying this number, you would use it as your effect size. So this basically determines what the meaningfulness of your data is. And it also tells you how much variance in one variable is accounted for by the variance in the other variable. There's also the coefficient of non-determination, which would be the alienation. That would be 1 minus r squared. This is the amount of unexplained variance as a whole. So in this practice question, a researcher wants to know if the ice cream sales is related to the temperature outside. Seeing as there is a chart on this slide, we can go and look at our variables and have the hypothesis and
Alternative hypothesis
yes.
formulated. Now, for our variables and hypothesis, our variables, our ice cream sales and temperature using degrees of Fahrenheit. And our hypothesis are our null is that ice cream sales and the temperature are not related or r equals 0, and that the alternative is ice cream sales and the temperature are related or r does not equal 0. So how we would do this in SPSS if we had to is that we would download the SPSS file, we would click Analyze, Correlate, then Bivariate. When you get to bivariate, you're gonna see basically a lot of spaces, but you really just need the variables box. And you would take your variables, insert your variables into the variables box, and then you will also make sure that Pearson is checked because Pearson is the correlation that we're using and not the other ones that might be listed. And a two-tailed is set to default as far as significance is concerned, so that's already done for you. And then you just click OK, and you would get something like this or relatively like this in your output window. And we've identified the R and the significance value, which you can see that R is 0.983 and that the p value is 0.000. But when you write this in APA format, you will not put that you can't put 0.000 because it can't equal 0. So therefore you would indicate that p is less than 0.001, which would still be valid.
And then you can go and to create a scatter point plot in SPSS. By doing so, you click Graphs, then head all the way down your bar to the Legacy Dialogues. Then click Scatter or Dot. Then, once you get there, you click the Simple Scatter, and then you define your X and Y's. You move the variables onto X and Y axes, and then click OK. Then it'll turn up with something similar to this. As we can see, we see all of our points plotted on the map. By looking at this, we can probably guess that there is a strong positive correlation. When calculating the effect size, we'd look at our correlation box that we got from SPSS and find R. Since R would equal 0.898, we would square that and get our effect size of 0.9604. That means that there's 96.04% chance of variance in ice cream sales that is accounted for by the change in temperature. When you do the alienation, you'd take 1 minus that and get 3.96% of the variance, which is that it is unexplained.
Now, what to report in APA is actually fairly simple. All you need is the Pearson correlation, or R, the degrees of freedom, which, if you remember, is also on the chart in the output window. But also remember that our degrees of freedom is calculated using n minus 2, not 1, or you'll get the wrong degrees of freedom. And that our p-value, which is a significant two-tailed test, is also in the chart. That is our that was our 0.000, but we will indicate it as p being less than 0.001. You also need the coefficient of the determination, which we calculated previously by hand, and it will not be used in SPSS. So make sure that you do that also. And some optional things that you can include are means and standard deviations for each variable, but it's not exactly necessary, especially for a small example such as this.
So what we would write in APA format would be answering the 3 questions of what did you do, what did you find, and what does this mean? So, being the end of this, which is in APA format, we did a Pearson correlation that we conducted to examine the relationship between ice cream sales and the change in temperature.
And what we found is that this positive relationship was found to be strong. You would input your answers from your output window into that area, and then of the variability in ice cream sales was found to be attributed to temperature change.
This means that the results can then show that there is a positive association between ice cream sales and the temperature, and that there will be more ice cream sales bought as the temperature rises. And since that was basically all we really needed to do for this assignment,
then that's all you needed for your APA format. And that brings us to the end of our presentation. We hope this cleared up some things about correlation, any questions that you may have had. I hope we did a fairly good job, me and Anne. And yeah.
If you need, take any questions down into the comments. When in doubt, you can email us on the classroom in Canvas. But this is what we have so far. Thanks for watching, guys.
And good luck on finals.